Okay, so let's take a look at another question where we're determining the intermolecular forces found in C3H6O. Now, what this molecule actually is, looks like this. And this molecule is known as acetone. That's kind of the common name, but we're going to call this propanone. And you'll understand this if you've done some organic chemistry. So all of you who understand how the structure gets created, you can skip through the formulation of the structure. But what we want to do is let's go through this step by step. And we'll also kind of list the bond angles associated with this VSEPR structure and so forth. Okay, so we're going to call this acetone because acetone is really commonly used polar substance that's, it's used to clean vials or beakers, right? It's highly polar. You'll probably have used it in the lab. And in this case, you also will hear about acetone found in nail polish remover as essentially one of the key ingredients behind it, right? So by looking at the structure, let's start with determining, okay, what is your central atom? Well, you're going to have multiple central atoms here, guys, right? So in order for us to kind of do that, let's figure out the total number of bonds. So we can skip the first step because there's going to be multiple central atoms. I think you'll see this better when we look at a potential rearrangement of this, or arrangement of the structure, right? So let's start by looking at the valence electrons of each species, right? So there's carbon here, there's a hydrogen, there's an oxygen, there's 3 carbons, there is 6 hydrogens, there's 1 oxygen. There is total number of electrons that each of them needs to have a stable octet, and we're going to also be looking at the total number of electrons in the valence shell. Okay, so each atom here, the carbon should have 4 valence electrons, the hydrogen should have 1, the oxygen should have 6. So to form a stable octet, each carbon should have 8 because there is 3 of them. I'm going to multiply this by 3, right? So that's 24. Each hydrogen should have 2, so if there's 6 of them, I'm going to multiply this by 6, that's 12. And this oxygen here should have essentially 8, right? So if we add this up, you can see that, the number of electrons we're working with is a lot higher, right? So in this case, 24 plus 12 is 36, plus 8, that's 44. Valence electrons, the carbon has 4 times 3, that's 12. This hydrogen here has 1 times 6, which is going to give us 6, and this oxygen here is going to have 6. So if we add all this up, we get 24. The total number of bonds is equal to the total number of electrons in the stable octet minus the total number of valence electrons, which is basically 44 minus 24, and we're going to divide this by 2. That's the formula, right? So if we divide this by 2, this is going to give us 20 over 2, which is 10. We should see 10 total bonds. So this is where we could do a little bit of trial and error, right? You need to understand that each carbon should have a total of 4 bonds. They're tetravalent, right? Each hydrogen should only have 1 bond, it's monovalent, and each oxygen should have a total of 2 bonds, it's divalent, right? So let's think about a potential structure of that, right? And you can imagine, the structure, there's going to be multiple central atoms, right? So we'll say one of the structures for the carbon could have these 3 hydrogens, right? The other structure at the very end could have 3 hydrogens, and this carbon could be double bonded with the oxygen, and each carbon could be attached to each other carbon with a single bond. Okay, so this is the only proposed structure that works, and you have 1, 2, 3, 4. This counts as 2, so that's 6, 7, 8, 9, 10. So that's 10 bonds. So you're going to have to play around with this, guys, to try to think about how this structure can work. So this is kind of the structural, but if we were going to show this using the Lewis dot structure, right, how you draw this out, right, it would look like, so each carbon, I guess I'll show the different central atoms, right? We'll call this central atom 1, central atom 2, central atom 3, right? So this is, we'll call this central atom 2, right? There's going to be 2 electrons here. I'll change the colors for each of the central atoms of carbon, right? So this is the double bond with the oxygen. This other central atom of carbon, let's say it's here, looks like that, right? maybe it looks like this, and we have a hydrogen here, hydrogen, 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 and we have another central atom that looks like this. Let's make this carbon in yellow, right? So you can see how all of this gets portrayed out, right? So then we have a hydrogen here, hydrogen, and hydrogen. You can see that the bonding architecture is fulfilled, although it is a little complicated to look at. Hopefully, if you've done some organic chemistry, you can also see how to convey some of these structures. These are groups of molecules. They're called ketones, right? So they all have this carbonyl group, which is the C double bond with the O. And the other thing we need to look at, so this is central atom 1, central atom 2, central atom 3. If we look at each central atom, and what you can actually see to design the VSEPR structure, I think if you take a look at the structural, which we saw here in this step here, it's actually a lot easier to look at the structural. None of these have lone pairs on the central atom. We're looking at central atom 1, and we're looking at each central atom in terms of lone pairs, bonding atoms, and the electron groups, which is the sum of the bonding atoms plus the lone pairs, right? Central atom 1 is going to have 0 lone pairs. It's going to have 1, 2, 3, 4 bonding atoms, and it's going to have a total number of electron groups is 4, so this is going to be a tetrahedral electron geometry and tetrahedral molecular shape. Central atom 2 is going to have 0 lone pairs, but now it has 3 bonding atoms because there is a double bond with an oxygen and 2 single bonds with each carbon on the left and right side. And then we have a total of 3, so this is Trigonal Planar. And then central atom 3 has basically the same setup as central atom 1, right? It has 4 bonding atoms, 0 lone pairs, and a 4. So it has exactly the same bonding architecture as central atom 1. So we can also expect it to be tetrahedral. Right, so technically if we're going to draw this structure using its VSEPR structure, right, the central atom 2 should be trigonal planar. So this is 120 degrees, this is 120 degrees. Right, central atom 1 should be tetrahedral, so I'm going to put one of the hydrogens in the plane of the page, and this carbon bond here is already in the plane of the page. Right, so then I'm going to put one hydrogen that is coming out of the plane of the page, one that's going into the plane of the page. Right, and this bond here should be 109.5 degrees. And then the other central atom 3 should mimic that same idea, right? So this would be hydrogen, and then this would be out of the plane of the page. This would be into the plane of the page. Okay. Now, based on this structure that we've drawn, I'm going to add the lone pairs of oxygen. Now what we could do, after we have the VSEPR structure, which we've generated here, this is your VSEPR structure. You can see there's multiple different VSEPR structures here. A combination of tetrahedral, trigonal planar, as well as another tetrahedral. Then we need to assess the electronegativity difference. Now, thankfully for us, we only have to look at really 2 different types of bonds, right? We just have to look at the electronegativity between carbon to oxygen double bond, the carbonyl group, as well as the electronegativity difference between carbon and hydrogen. Because we know the difference between carbons will be 0. So this makes our job a lot easier. I'm going to use these same values that I posted up in the previous videos for the electronegativity if you want to take a look at those videos, right? You can get these values from the Pauling scale, guys, right? So electronegativity of carbon we're going to be using is 2.55. The electronegativity of oxygen we're going to be using is 3.44. And the electronegativity of hydrogen we're going to be using is 2.20. And the 2 electronegativity differences that we're going to be using in terms of our intervals or our criteria to determine if it's a non-polar covalent bond versus a polar covalent bond is between 0 and 0.45. This is a non-polar covalent bond, and the electronegativity difference, if it's greater than 0.45, we'll just kind of separate this, and it's less than 1.7, this is a polar covalent bond. Okay, so Let's do the calculations here. So in this scenario, if we do electronegativity difference between this bond here, the carbon double bond with the oxygen, we do electronegativity of oxygen minus the electronegativity of carbon, which is 3.44 minus 2.55, which is 0.89. This tells us that we have a polar covalent bond. So there is a dipole moment being created. So the dipole moment, the vector arrow, should be pointing this way. Okay, so you guys can see how the dipole moment gets created. This is partial positive. This is partial negative. And between the carbon and the hydrogen, we do electronegativity of carbon minus electronegativity of hydrogen. We get 2.55 minus 2.20, which is 0.35, right? And this is basically a non-polar covalent bond. So there is no dipole moment created. So net dipole moment is in fact this dipole here. This is your net dipole moment. There's only one vector here. This tells us that this is a dipole molecule. So this is polar, right? And if this is polar, well, because we have a carbon and oxygen, and if we're binding to other molecules, we should see the intermolecular forces that include London dispersion forces and dipole-dipole forces. In cohesive forces, or cohesive bonds, that means bonds between the same molecules, you're not going to see hydrogen bonding, right? Maybe if you had this dissolve in water, then you will see hydrogen bonding. This is one of the reasons why acetone, it actually is more soluble in water than it is with other acetone molecules. Okay, so if you look at these steps that we kind of took here, right? We did electronegativity calculations, right? Then we generated the dipole forces here, and this was step 7 where we looked at the intermolecular forces. The reason I didn't write hydrogen bonding here is because if you think about acetone binding with another acetone, let's say there's another acetone molecule here. So if I have space, so I'm going to write this as CH3 because we're not really looking at it. All right, this is partial negative and this is partial positive, right? You wouldn't get hydrogen bonding. You would just get a dipole-dipole force here, right? So that's why these are the intermolecular forces found in acetone. So in the next video, what we're going to do is we're going to compare the last 4 molecules, well, including this one, these 4 molecules in terms of a particular physical property. We're going to be looking at the boiling point, and we're going to kind of see how they relate to each other in terms of going from weakest to strongest intermolecular forces and therefore boiling point. So stay tuned for that video. I would highly recommend you guys to watch that. If you didn't understand anything in this video, or if you didn't understand certain aspects of this video, take a look at the video that I'm going to attach to the end of this. It's going to be a complete overview of Lewis dot structures, VSEPR, the different types of intermolecular forces in detail, as well as some sample questions. Some of the sample questions might be recycled from the ones seen here, but it's always nice to view something with a different lens. Okay. All right, guys. Well, thanks for tuning in, and until the next time, stay tuned for more instructional videos. Congratulations on finishing the video. To reward your attention and determination to learn and enhance your skills, we've created a new reward system this year. Each time you complete a video, you will be rewarded IQ points. Depending on the length, difficulty, and type of video, instructional versus question-based or both, you can be rewarded different levels of IQ points. These IQ point rewards will be either 10, 20, 50, or 100 points. Our goal for implementing this system is to enhance your motivation and improve your daily productivity. Use the amount of IQ points you earn each day to reinforce and gauge your commitment towards your education. And while you do this, remember to like, comment, subscribe, and share our videos. Your continued support will assist us to release more free educational content in the future. Our collective goal at Course Concepts is to assist you towards academic success, one step at a time, because success starts with a single concept. So we want to thank you for being a member of Course Concepts.